derivative to find the tangent in parametric form. However, the derivative in parametric form is defined in a little different way than we defined it back in calculus 1. You know, just take the derivative, dy dx, f prime, whatever notation you use. Because in this case, this set of parametric equations describes, or rather is described by two separate equations. An f equation that depends on t, f of t, and a g equation or a y equation that depends on a g, both of them depending on t again. This t is a new variable, it's a third-party variable governing the whole system this time. That's telling us when, again, parametric equations are not just telling us where as opposed to rectangular equations. So parametric equation tells us where and also when. All right, so two pieces of information. And in this case, well, we need to take the derivative of both equations and find the quotient between the derivative of the y equation and the derivative of the x equation. Provided, check this out, provided that the derivative in the denominator, the dx dt, is not 0 because, well, you know the whole story when dividing by 0, right? We would get an undefined quantity here. So, the first derivative, even though we denoted dy dx, it's a function of t. You'll see how is it going to work on the in the examples. And other pieces of information that you might want to find useful, once you get this derivative, you will get a quotient in this case. So, and in this case, the curve, so we can find the horizontal tangencies when the derivative, well, or rather when the numerator of the derivative equals to 0, and vertical tangencies when the denominator of the derivative is equal to 0. Just set the equations equal to 0 on both cases. That's all we do. All right. So the second derivative is going to be a little tricky. So the second derivative, it's essentially the derivative of the derivative, and in this case, well, it's the derivative of what we got in the first instance, in the first iteration of the derivative, divided by the derivative of the x equation. Well, right now, the symbols or the way we're going to get them, it looks a little weird, but it's going to make more sense once we get to the example, which is actually right now. So,
I thought you people also use x as with the dot on top to denote x over dt.
yeah, so that's a notation from physics and from differential equations, and you use that dot at the top when you're talking about the kinematics. In this case, it's related to, we can use that notation as well. But that's more like a physics notation, but it denotes the same thing. Mm-hmm. Yeah. Mm-hmm. All right. Given the curve represented by the equations x equals t squared and y equals to 3t minus 5, find the slope of the curve at a time t equals to 2. So, well, this is like the straightforward type of problem, you know, in which we just gonna start with the equations. X equals to t squared and y equals to 3t minus 5. So they're asking us to find the slope, and in order to find the slope, we need to take a derivative, and the derivative in parametric form involves finding two derivatives. That is, the derivative of the x equation with respect to t and the derivative of the y equation with respect to t. So let's go ahead and do that. That is, that means dx dt equals to 2t, and dy dt equals to 3. All right, so we can form our derivative dy dx by dividing the derivative of y with respect t by the derivative of x with respect t. Well, just writing down where they correspond, that's going to be a 3 over 2t. And we can use this expression to find the slope at any particular time for this set of parametric equations. And in particular, they're actually asking us to find the slope when after 2 seconds traveled by the particle along this path. Well, the way to denote this is, write down dy dx. With this bar, recall that this bar means evaluate at, it looks like the bar from the integration from a to b, but in this case, we just denote this at t equals to 2. And all we do is simply substitute the number 2, whatever you see the letter t. So that's 2 times, 2 times, this is a 3, right? 2 times 2, and that's a 3/4. So 3/4 is the value of the slope at that given time, right? So very straightforward. Just take a couple of derivatives, and just be careful of dividing in the correct order. dy over dt, dy dt over dx dt, not the reverse. All right. So let's see. What about this? So what's the next example? So actually part B. So find the slope of the curve, letter B, at the point 9, 4. So at the point 9, 4. So notice in this case they're not telling us the value of t. In this case they're giving us an ordered pair. And if you think about the derivative, yes, even though the derivative is dy dx, we're finding the change of y with respect to x. However, this is an expression of t. But again, recall that t and the order pairs x and y are related by or through the set of parametric equations. Well, in this case, we need to know when is the particle at the point 9, 4. And in order to do that, let me write the set of parametric equations again. X equals t squared and y equals to 3t minus 5. So this is what we're going to do. We're going to set each parametric equation equal to the corresponding value. That is, the x equation, set it to the corresponding x value in the point, and the y value, the y equation, set it equal to the y value in the given order pair. And this is going to create in some sort of a system of equations. It's not necessarily a system of equations because it's only one variable, and in this particular situation is the variable t. All right, so let's set 9 equals to t squared and 4 equals to 3t minus 5. And in this case, let me keep highlighting all these numbers, all these quantities, so you can see where and what am I substituting with, all right? So this will create two equations that we will solve. So number 1, t squared equals to 9 and 3t minus 5 equals to 4. That means t equals plus or minus the square root of 3, the square root of 9, and t equals negative 3, 3. On the other hand, for the second equation, 3t equals to, add 5 to both sides, that's going to give us a 9, and 3t, and t equals to 3. So, which value are we going to take? So in this case, the value that we will take is that one that repeats, or not the repeat, that one that is common to both. So let me give you another way to get this done. It's a lot quicker, but a shorter way to do this is just solve for t on the easiest of the equations. In this case, the easiest of the equation is the second equation because it's a linear equation. It's going to give us one single value as opposed to also solve the quadratic equation. Yes?
T equals negative 3 also does not work because you can't have a negative time.
Exactly. So that's no, it's still time. It's still okay to get negative times because ultimately it's some sort of a reference. So, even if you, of course there's going to be an initial time, right? So you will still have a set of order pairs of what could have happened if we had negative times. But again, those negative times could be turned into positive times depending on how we parameterize the equation. So that's a good question, right? So, but the thing here is just to make sure that you get the same value repeated or common into as a solution to both equations. Well, my advice is solve both, but if you want to do it the quicker way, just solve the easiest of the equations. In this case, the linear one. All right. So now that we know what's the time, that means t equals to 3. We may go ahead and evaluate the derivative at the value t equals to 3, that is dy dx, evaluated at t equals to 3, and in this case, well, this is 3 times 2 times t. Well, in this case, it's t equals to 3. We may cancel these 3's, and the final answer here is 1/2. So that's the slope along this set of parametric equations at the point 9, 4, which corresponds to the value of t equals to 1/2. All right. So let's see. Find the second derivative. For the second derivative, number 1. Well, let me write down the formula first. That's the one that could be a little tricky. So I'm gonna go d. So take the derivative of the already first derivative and keep dividing by dx dt. Okay? Now, so we already have a derivative dy dx, so we can replace this with, okay, that's d dt times d dy dx, which we got from the first part. That's 3 over 2t. And then divide by dx dt, that part we also got it from the first part, from part A. And what we got for that part, that's 2t, right? Okay, so be careful when taking the derivative, because notice the variable t in the denominator of the numerator. I know that's kind of weird. So it's in the denominator, it has to go in the numerator first so we can differentiate it. We cannot just differentiate it like that. So that's ddt, and that's 3/2 t to the -1. Divide that by 2t. And just use the general power rule to differentiate this little term. Well, -3/2 t to the -2 over 2t. And well, there's a couple of things that you might want to do here. Well, number 1, have those negative exponents in the denominator as positive exponents to get a simpler result, and also this coefficient. But what about this coefficient? So number 1, we have this -3/2, but dividing by 2 is the same as multiplying by its reciprocal, which is 1/2. And what are we going to have here? 1 over t squared, which is the one we sent to the denominator with positive exponents, and multiply by t. And well, that's going to leave us with -3/4 times 1 over t cubed, and just clean it up by writing into a single quotient. And that's how we find the second derivative. Right? It's a little trickier, but actually we're essentially using the same results from the first derivative. We just put it together into a new formula, if you will. Okay. So let's see what's next. I think that's about it for this first example. Let's have a look at the second example question.
So, Professor, so find the third derivative, so we'll apply the same process.
Yes, but I don't have a formula. We need to describe a formula for that, which actually I don't have over here. But I guess it should be something like that. Just we would need to define. We need to define it. But yeah. All right. Another example. They're just asking us to find the first and second derivative for the curve, for the parametric curve, for the curve defined parametrically by these two equations. However, I would like to rewrite this so it's easier for you to identify the rules of differentiation that we're going to use in this case. So that is, I'm going to rewrite this sine t, or rather sine squared t, as sine to the second, as sine t to the second power. Well, in this case, that's so you can see that we're going to use the chain rule to differentiate the first equation. Well, so let's differentiate the first equation. That is, let me write dx dt and dy dt to differentiate the equations. That is, well, using chain rule, that's a 2 sine t times the derivative of sine, which is cosine t. And on the other hand, the derivative of the y equation, that's only the derivative of cosine, which is negative sine, right? So we got all the information we need to do the remaining parts, or to come up with information they're asking us for. In this case, first derivative and second derivative. So dy dx, which is the quotient of two derivatives with respect to t. That is dy dt over dx dt. So dy dt, which is negative sine t, over 2 sine t cosine t. And we're essentially done with the calculus for the first derivative. However, you might want to simplify this a bit further, because number one, we can cancel out the sine t's right here. So let's cancel them out. So that's going to be negative 1 over 2 cosine t, which at the same time is negative 1/2 secant t, using identity. So it would be better. So my advice, when you are being asked to find the first and the second derivative in parametric form, make sure to simplify your first derivative as much as possible, because when it comes to getting the second derivative, that implies finding the derivative of what we got in the first part, and if you didn't simplify that, it's just going to turn into madness here. So do you want to do a quotient rule with this that also involves another product rule? You don't want to do that. And well, you can think of these 2 sine theta cosine theta as sine of 2t, right? Not theta, t rather. And you can get, in this case, negative sine t over sine 2t. That's still correct. That's technically correct because we're using the trigonometric identities. However, you don't need to do all this, because you are going to end up with a quotient of the function. So when you get to the second derivative, again, you don't want to deal with a quotient rule, right? So, I mean, if you want to do that for practice, that's fine. However, my advice, just keep it simple and try to simplify this first derivative as much as possible. So let's get to the second derivative, and the second derivative. So that is the derivative of the already first derivative divided by the derivative of the x equation with respect to t, which is information that we got. Number one, well, actually both pieces of information, we got them from the first part of our solution here. So, which one? Oh, this one right here, right? dy squared, yeah, d squared y. Oh, yeah, this one right here, right? Yes, dy dx. Yeah, thank you. All right, so dy dx, which in this case is this quantity we got in the first part right here. Let's substitute there. That's going to be d dt, and that's negative 1/2 secant t, divided by dx dt, which we got from the first part. That's 2 sine t cosine t. Well, let's take the derivative in the numerator. Differentiate negative 1/2 sine, secant t. Well, what's the derivative of secant? Anybody remember that one? Secant tangent. All right, secant tangent. Times the negative 1/2 secant tangent, and divided by 2 sine t cosine t. So there's a few things that we can still do about it. Number one, so I'm worried about the coefficients first. Let's do that part first. So negative 1/2 divided by 2 is the same as saying negative 1/2 times the reciprocal of 2, which is 1/2. At the same time, I would like to rewrite this secant and tangent functions using identities, that is in terms of sine and cosine, so we can simplify this a lot better. So I'm going to write this secant. This secant is the same as saying cosine in the denominator. The reciprocal of secant is the reciprocal of cosine and vice versa. And I'm going to leave this sine t, cosine t the way they are. And I'm going to write this tangent as sine t over cosine t. So in this case, well, let me just highlight the way they came from. So this tangent became sine over cosine, and this secant became 1 over cosine, that is a cosine in the denominator. Just so you can see where is everything coming from. Well, we can actually simplify a lot. Number one, well, not a lot, sine and sine, we can divide out those two. And that's, well, number one, negative 1/4. And we're going to be left with the quantity 1 in the numerator, cosine times cosine times cosine. That's essentially negative 1 over 4 cosine cubed t. Well, we can leave it like this, or we can write it in a nicer way. We can write those cosines this cosine in the denominator towards the numerator as negative 1/4 secant cubed of t. And that's final answer. Right, well, in this case, they're not asking us to compute at the value where t equals to 5, t equals to 9. Well, in this case, pi over 2, I guess, pi, 2 pi, etc., right? Multiple, in this case, for different angles, because we have trigonometric functions. All right, so again, this is how we compute derivatives and second derivatives. So careful, it's a little more than just taking the y dx. You know, we need to consider two parts essentially. All right. Let's get started with one more example here. Well, find the slope, the equation of the tangent line, and describe the concavity for the curve given by x equals to t squared minus t, and y equals to t cubed. All right? So, that's basically calculus 1 problem in which we are going to look at analyzing the whole function. But in this case, we're going to do this in parametric form. So let's recall all the pieces of information. Well, slope. How do we get the slope? Well, find the derivative. We know how to find a derivative in parametric form and evaluate it at the given value, which, by the way, I didn't type, at t equals to 2. I forgot to type that part, all right? It's when t equals to 2. So otherwise, well, how we're going to do this, right? And, well, essentially for the next part, okay, finding the equation of the tangent line involves two pieces of information. Again, to get the equation of the tangent line, or the equation of a line in general, we need two pieces of information. That is the slope and 1 point. Well, we don't have any of them, but we can get this. Well, number one, the slope from the derivative, and the point, well, we're not given a point. We're given a value of t in this case, and we're going to get the point from that value of t. And for concavity, for the third part of the problem, we will use the second derivative. Recall that concavity is described by the second derivative. Whenever the second derivative is negative, we know our function is concave down. Otherwise, when the second derivative is positive, the derivative, when the second derivative is positive, is concave up. Yes?
I thought concavity was described by the third derivative.
The third? No, it's by the second derivative. The first derivative tells us where the function is increasing or decreasing to get a maximum or a minimum, while the second derivative describes concavity. And if there, well, in most cases, if there's a change in concavity, there is a point of inflection. Third derivative, I don't think there's any physical application other than just keep taking derivatives and derivatives. All right, let's get started with finding the derivatives here. So that is dy dx. Oh wait, hold on. Let me take the derivatives in. So dx dt, dy dt. So that's going to be 2t minus 1. That's using general power rule. And the derivative of the y equation, that's a 3t squared. All right, so let's see. Let's find dy dx. Dy dx, which is the quotient dy dt divided by dx dt. All right. So the dy dt in this case is 3t squared divided by the dx dt, which is 2t minus 1. Well, in this case, there's nothing we can simplify like a common factor or a numerical common factor or like a power of t, etc. So that's the simplest we can go about it. All right. So now that we have this first derivative, how about we evaluate this first derivative, dy dx, at the point where t equals to 2 in this case, right? In this case, we're going to do a straightforward calculation. We're not given a point for which we have to find the point for, the value of t first. We're given the value of t, which is great. So that's going to be 3 times 2 squared divided by 2 times 2 minus 1. And well, what do we have in the numerator? So that's 2 squared, which is 4, times 3. That equals to 12 in the numerator, divided by 2 times 2, which equals to 4, minus 1, that equals to 3. And simplifying this, the slope equals to 4. So we have the first piece of information that we need in order to get the equation of a tangent line, that is the slope. And well, usually the one that takes the longest, and because we had to take a couple of derivatives. So, and then we need a point. But how do we get the point? We're not given a point. But recall that there is a connection between t and the set of parametric equations. Those parametric equations are going to give us the position x, y for every single value of t that you can think of in this case. Well, as long as they are in the domain. But in this case, I don't think there's any issues with the domain because they're all polynomials. Just like last time we discussed a problem in which the parameterization had a square root of t. Well, in that case, we have issues with the domain. We had restrictions in the domain. No restrictions here. All right, so all we have to do is simply evaluate x at 2 and y at 2. And that's going to be 2 squared minus 2. What I'm doing is substituting in the original parametric equations, and 2 cubed. That's going to give us 2 squared, which is 4. 4 minus 2 equals to 2, and 2 cubed, which is 8. So that is at t equal to 2, we are, well, so the particle because again, well, I'm just calling it in a very generic way a particle, because this set of parametric equations describe the motion of a particle along some path described by the equations, and in this case at different particular time. So the particle is at the point 2,8 when t equals to 2. That is, well, depending on the context, if it's like a rocket, if it's a car, well, after 2 seconds, maybe after 2 minutes, maybe depending on Now, again, depending on the context, maybe 2 years, maybe 2 centuries, well, depending if it's like a comet, those things that we get to see, every 100 years, right? So, again, that depends on the context. So, we have the point, we have the slope, we can use the point slope form, that is, y minus y1 equals m times x minus x1, where y1 is the y value of the given point and x1 is the x value of the given point. M is the slope that we just found via differentiation in this case. So y equals to, y minus y1, which is y minus 8, equals m, which is 4, times x minus 2. And well, you know the drill to get this equation simplified. Distribute the 4. Y minus 8 equals to 4x minus 8, and we can simply cancel these two 8s, and that's going to give us the graph of y equals to 4x. All right. So that's the first part of this exercise, the first part of the problem. Well, so just so you guys don't feel like we are just crunching numbers and symbols, well, we're essentially doing that. How about we get a visual of this? Well, yes?
Isn't the value of the x have to be 2 squared minus 1?
2 squared minus 1 over here? Oh, but that's for the derivative. Do you mean when finding the point?
Yeah.
Oh, because we're finding the point, the position, using the position function. In this case, the derivative would essentially be the velocity function. And the second derivative would be the acceleration function. So we need to know where that is positioned when t equals to 2. All right? Now, so how are we going to do this? Because number one, check the original example. The original exercise. The original exercise is given in parametric form. All right? It's given in parametric form. Well, we would go to our graphing calculators, use parametric form, and type the equations. However, the equation of the tangent line right here, it's not in parametric form, unfortunately. It's actually in rectangular form. So the issue with this is that you would have to graph the parametric equations in one mode and the linear equation in another mode, but you wouldn't be able to see both equations in the same plane. So there's a couple of things that you might want to do. Number one, you could eliminate the parameter from the set of parametric equations, which is going to take a good minute because check that out. Try to find out the easiest of the equations, and I don't think there's any easier. Maybe the easiest is y equals to t cubed. Take the cube root and substitute the cube root in the original equation, but that's going to give us an x equation that depends on y, and we cannot graph equations, or rather functions of y in our graphing calculator. All we graph is functions of x. In fact, we use parametric mode to graph those equations or those functions that depend on y when the y is the independent and the x is the dependent variable. So in this case, it would be a lot easier to parameterize the second equation, the y equals to 4x, because it's just the equation of a line. All right, it's just the equation of a line, and in this case, x and y. Recall that the traditional way to parameterize a rectangular function is to give t to the independent variable, and in this case the independent variable is x, and well, that'll be 4 times x, which is just 4t. So this is what we're going to put together in our graphing calculator. These two sets of parametric equations. Number one, the one that I highlighted in green, and the one that I'm going to highlight in yellow. All right? We're going to graph these two together. And you'll see how this indeed is going to be tangent to the original function. So let's see. I'm going to go to my graphing calculator. Again, you might want to go to parametric mode. And well, in this case, again, as opposed to having a y1, y2, y3, in this case, we're going to have x1, y1 for the first set of parametric equations, x2, y2 for the second, x2, y3, etc. So Let me type the original equation. That's t squared minus t, and y is t cubed. And well, let's type the second set of parametric equations, which in this case is the equation of the tangent line. And we said that is t and 4t. All right, and let's graph them together. So the graph of the actual parametric equation. Well, number one, let me hide this one for. Let me hide the second for a little bit. The graph of the original function t squared minus t and y t cubed, it's kind of a weird one. It sort of starts at the origin, and it does that. Actually, let's see the direction in which it goes. Let me do 0.01 and graph. Actually, it went from like left to right. All right, and let's see. Let me graph as well. Okay, all right, that's going to show this time. And notice at the point 2, comma, 1, 2, 3, 4, 5, 6, 7, 8, here is where we have the point of tangency, all right? So in this case, yes, we need to have either two parametric equations or two rectangular equations. And again, coming back to the example, there's no way we can eliminate the parameter over here so we can get a function of x. In fact, with that eliminating the parameter in the original equation would give us a function of y, which we cannot do in our graphing calculator. Well, maybe there's other graphing utilities online that may do that for you, but you still, well, in that case, you would have to also define this as a function of y, that is x equals to 1/4 y. But well, let's keep it simple to only functions of x. All right, and